Okay, thanks, Rio. So yeah, like you said, I'm going to be talking about these hidden variable models for quantum computation with magic states. So these are the primary references. So there's a few different results. First, we had a result for qubits only, and then we sort of found a bit more structure about these results. And then more recently, we extended these results to apply to qudits of any dimensions, not just qubits. And this joint work with Jian, who talked earlier today, and Robert, as well as Arne Heimendal in Cologne. So here's an overview of what I'm going to talk about. So I'm going to start with some motivation. So I'll go through sort of why we want to talk about hidden variable models and classical simulation algorithms for quantum computation. Then I'm going to review some background material. So I think it should be familiar to everyone already, but just to make sure we're all on the same page with the definitions. And then I'm going to spend some time talking about classical simulation algorithms for quantum computation based on quasi-probability representations. And I'm going to spend some time there. The reason being, my goal here isn't really to go through our main results in full excruciating detail. The proofs are in the papers if you want to know more, or we can talk later if you want to know more. My goal is more to give some background on where these models came from and why we think they're interesting and why we think we should want to talk about them. So then after that, I'll move on to the main results and give our main results, which is these hidden variable models and classical simulation algorithms for quantum computation based on these lambda polytopes. Okay, so first, the big question we want to address for this is this question: what makes quantum computation better than classical computation? So we know there are some problems, some applications where quantum computation is more efficient or outperforms classical computation, and it would help if we could better understand why. So the way we do this is we look at subtheories of quantum theory that we can simulate efficiently, because we know that anything we can simulate efficiently on a classical computer is not really useful for full universal quantum computation. And so anything that we can't simulate efficiently might be useful. So this is our general method for approaching this question. So here's a simple motivating example. So consider this quantum circuit where we have first preparation of an unentangled initial state, followed by a sequence of local unitary gates on each qubit. And then we end with a measurement of each qubit in the computational basis. So everything here can be simulated efficiently on a classical computer, and in the obvious way, just by tracking each qubit separately. So we're doing, linear algebra in a two-dimensional space, and we just do it n times over. So everything here can be simulated efficiently classically. And what we can conclude from this is that entanglement is necessary for a quantum computational advantage. So that can take different forms. For example, in MBQC, it would be an entangled initial state, or in the circuit model, you'd have some kind of entangling gates, but in some form, entanglement is necessary. So to go through these more general methods that I'm going to talk about later, we need to start by going through some background material. So I think this is familiar to everyone, but we'll just go through the definitions anyway. First definitions we need is the stabilizer subtheory. But this is a subtheory of quantum theory consisting of three things. So we have stabilizer states, Clifford gates, and Pauli measurements. So this is enough already to do quite a lot of stuff. You can define quantum circuits. We have everything here we need to define quantum circuits. But this isn't quite good enough for full quantum computation, because we have the Gauss-Minnel theorem, which says that any quantum circuit consisting of just these three things, the stabilizer states and Clifford gates and the Pauli measurements, this can all be simulated efficiently on a classical computer. So what we can conclude from this is that we need some kind of non-stabilizer resources, something that lies outside the scope of the stabilizer subtheory for universal quantum computation. And in the model of quantum computation that we're going to be talking about, that is some kind of non-stabilizer input state. So this is the magic state model of quantum computation, which I'll call QCM for short. So in this model, we restrict to just the operations from the stabilizer subtheory, so Clifford gates and Pauli measurements, but we include extra input states. So rather than only allowing stabilizer states, we allow some non-stabilizer input states. And this allows us to perform universal quantum computation. Here's an example of how it works. This is the same teleportation circuit that Nadish talked about yesterday. By including this extra magic input state and then performing only stabilizer operations, we can effectively implement a T-gate. And since, as everyone knows, the Clifford plus T-gate set is universal, this shows that this magic state model is universal for quantum computation. So since the operations of the stabilizer subtheory by themselves aren't universal, but they're promoted to universality by including magic states, we can say that the computational power of quantum computation is in the states. And then a question we can ask is, which states are useful for QCM? So you can think of this as kind of a refinement of the question I asked earlier. So that question being, what makes quantum computation better? That's kind of a vague, abstract question. This is a way of making it more concrete. So we focus on this model because then we can just focus on the states and ask which states are useful for QCM. Any questions so far before we move on? Okay. So I need to go into a little bit more detail. So remember, stabilizer subtheory consists of three parts: Pauli measurements, Clifford gates, and stabilizer states. The first, Pauli measurements. So we're not assuming qubits here. We're talking about qudits of any dimension. So in a d-dimensional Hilbert space, we have these generalized Pauli operators, an x and a z. In the qubit case, these reduce to just the standard qubit Pauli operators. If we have multiple qudits, so the n-qudit Pauli group is generated by tensor products of these operators acting on n qudits. And if we mod out overall phases, we have this isomorphism. So the n-qudit Pauli group up to overall phases is isomorphic to zd to the 2n. And so because of this, it only takes O of n bits to specify a Pauli operator. I think this should still be familiar to most people. The Clifford gates, so these are the unitary operations allowed in the model. They come from the Clifford group, which is the normalizer of the Pauli group in the unitary group up to overall phases. And we have similar kind of isomorphism. So the Clifford group, elements of the Clifford group can be associated with symplectic maps on this finite dimensional vector space, finite dimensional vector space over a finite field. And then the last thing we need is stabilizer states. And this is one way of defining them. A stabilizer state is any state reachable through a circuit of this form, the Clifford gates plus Pauli measurements acting on a zero initialized state. Okay. So these are all the definitions we need. Remember, this is the question we want to ask, or a question we want to answer is which states are useful for QCM. One way of approaching this question comes from quasi-probability representations. And one of the more famous examples of this is the odd dimensional discrete Wigner function. So this is Gross's Wigner function that came up in David's talk this morning. So I'm going to go through a slightly different definition than was introduced there, but it is equivalent. So first we define a phase space, which consists of all non-contextual value assignment functions on the set of Pauli observables. So to be more explicit, these are functions from the Pauli observables to the eigenvalues of the Pauli observables, satisfying these two non-contextuality conditions. So first, the identity gets assigned to 1, and then the value assigned to product of two Pauli observables is equal to the product of the value assigned to each of the observables. So this is our non-contextuality condition. Each point in phase space is associated with one of these non-contextual value assignment functions. And then we can identify points in phase space with these phase space point operators. So this is a sum over all the Pauli observables weighted by this non-contextual value assignment function. And you can think of this as an operator that has a definite value for each Pauli observable. So for any Pauli measurement you want to do, you'll get a fixed outcome. Now we can define the odd dimensional discrete Wigner function. So remember, this is the definition of the phase point operators. These operators form a basis for the space Perm of H, which is the vector space of Hermitian operators on the n-qudit Hilbert space. And since they form a basis, any density operator can be expanded in this basis. And it's these coefficients in this expansion that we call the discrete Wigner function. So maybe one more thing to say. These operators also have unit trace. So if you take a trace of this equation, you end up with 1 on the left-hand side. On the right-hand side, you end up with the sum of all these coefficients. So the sum of the coefficients is 1. This is why we call it a quasi-probability representation. This along with a few other reasons. Here are a couple of examples. In the case of a stabilizer state, so this is something Paulina mentioned on Monday, all stabilizer states have non-negative Wigner functions. So when the Wigner function is non-negative, it really is just a probability distribution. But there are other examples of states, magic states, for example, for which the Wigner function is negative. It takes some negative values. So in that case, it's not a probability distribution. It's only a quasi-probability distribution. The phase space has some properties that makes it useful for defining or for describing quantum computation for magic states. So in particular, it has some properties that mean it sort of behaves well under all the dynamics of QCM. So first, under Clifford gates, phase point operators map deterministically to other phase point operators under any Clifford group element. Or another way to say this is the Wigner function is Clifford covariant. This is something Paulina talked about on Monday as well. And the other dynamical operation is Pauli measurement. Under any Pauli measurement, phase point operators map to probabilistic combinations of phase point operators. And importantly, positivity of the Wigner function is preserved under both of these operations. So because we have these nice properties, the phase space behaves well under these dynamics, we get a simulation algorithm, a classical simulation algorithm for quantum computation with magic states. And it applies whenever the Wigner function of the input state is non-negative. So in that case, it's just a probability distribution, and we can sample phase space points from it. So this is what we do. We start by sampling phase space points according to this probability distribution describing the input state. And then we just propagate these phase point operators through the circuit. And we have these deterministic update rules whenever you come to a Clifford gate. And we have probabilistic update rules whenever you come to a Pauli measurement. And we need one more thing when you come to a Pauli measurement, which is a measurement outcome. But remember, each point in phase space is associated with a deterministic, fixed outcome for each Pauli measurement. So you just return that value as your outcome. And this reproduces the predictions of quantum mechanics. So what does this tell us? Well, we have an efficient classical simulation algorithm for quantum computation whenever the Wigner function of the input state is non-negative. So this means that negativity in the Wigner function of the input state is a necessary condition for a quantum advantage in this model of QCM. Any questions so far? Okay. And we can think of this more geometrically. This is a picture I drew last night. In red, we have the set of, this not an accurate picture, it's just more like heuristic. In red, we have the pure quantum states. Anything inside the red circle is a mixed quantum state. And then we have this finite set of phase point operators. Anything inside the convex hull of these phase point operators, for example, this point over here, will have a non-negative Wigner function. And any quantum state that lies outside the convex hull of those operators will have some negativity. So it's the ones outside of this convex set that could be magic states. We can go a little bit further and talk about what happens when the Wigner function goes negative. So this is work that came out of the group in Sydney. So when the Wigner function goes negative, you still have a simulation algorithm based on amplitude estimation. But the number of samples required scales proportional to the square of this factor R, which is a measure of the amount of negativity in the Wigner function input state. So in this sense, negativity determines the cost of classical simulation. So everything I said so far only applies to QCM on odd dimensional qudits, which is kind of a strange distinction to make, but it's something that came up in Paulina's talk on Monday, as well as David's talk this morning. There's a handful of no-go results for why you can't define a similar result for even dimensional qudits. So first, as Paulina said, there's no Wigner function for even dimensional qudits, which is Clifford covariant. And there's no Wigner function for even dimensional qudits, which is positivity preserving under Pauli measurements. And then David Schmidt has this no-go result, which says there's no non-negative diagram preserving quasi-probability representation of stabilizer subtheory for even dimensional qudits. And then there's one more no-go result, also from the group in Sydney, which says it gives a memory lower bound of O of n squared bits required to simulate contextuality. So this kind of contextuality comes up in QCM on multiple qubits. So in order to simulate QCM on multiple qubits, you need O of n squared bits, whereas this construction with the Wigner function, you only need O of n bits. So this sort of tells us which direction to go in. We need to kind of expand our phase space if we want to simulate QCM. So the sort of standard definition of the Wigner function doesn't really work. We've got to modify it somehow. So here's the sort of properties of a quasi-probability representation I want in order to simulate QCM. So this is different from David's definition from earlier today, because I'm not assuming anything about diagram preservation. But this is the more useful definition for talking about quantum computation. So a quasi-probability representation of QCM is a set of operators, usually a finite set of operators in the space Herm sub 1 of H. So this is the space of trace 1 Hermitian operators on the Hilbert space, satisfying these three properties. So first, they have to span the space of Hermitian operators on the Hilbert space, and then they have to behave well with respect to the dynamics. So under any Clifford gate, phase point operators have to map to other phase point operators, and under any Pauli measurement. So your pi is a projector corresponding to a Pauli measurement, yielding some measurement outcome. If that outcome can occur, if you do that measurement on a phase point operator, meaning this trace inner product is positive, then the post measurement state you get has to lie inside the convex hull of these operators. So this gives your probabilistic update rules under Pauli measurements. So you can unpack this a little bit. Because of the first property, because the span of the operators is the space of Hermitian operators on the Hilbert space, any state rho can be decomposed as a linear combination of these operators. And actually, these coefficients are going to be real. And taking a trace of this equation, get the 1 on the left-hand side, and on the right, just the sum over the coefficients. So this is actually an affine decomposition. So this is, again, why we call it a quasi-probability representation. So here's an example from a few years ago. So any state can be decomposed as a affine combination of projectors on the stabilizer states. And stabilizer states satisfy the other two properties as well. So if you conjugate a projector onto a stabilizer state by a Clifford gate, you just get another stabilizer state. And also, obviously, if you perform some Pauli measurement on a stabilizer state, you also get some probabilistic combination of stabilizer states. So this satisfies all the properties we need. And this also yields a classical simulation algorithm, similar to the one before. Whenever this description of the state is non-negative, it's just a probability distribution. And so we can sample stabilizer states according to this probability distribution, and then propagate the stabilizer states through the circuit using these deterministic and probabilistic update rules. And we have a geometric picture for this one as well. So again, in red is the set of pure quantum states. Everything inside the circle is a mixed quantum state. And this diamond shape represents the stabilizer polytope, or the convex hull of stabilizer states. So we have a finite number of pure stabilizer states, and anything that can be written as a convex combination of stabilizer states is a stabilizer mixture. Any questions so far? Nope. So we can go a little bit further than this. This is an idea that came out of this group a couple of years ago. This is another way of extending the odd dimensional Wigner function to qubits, or to even dimensional qudits. So I didn't say this explicitly, but the thing that goes wrong when you try to extend that definition to qudits, or even dimensional qudits, is contextuality. So remember, in the odd dimensional case, phase point operators were associated with these non-contextual value assignments. Well, for even dimensional Pauli observables, we have Berman square type proofs, which say that these non-contextual value assignments don't exist. So rather than sort of identifying phase space points with non-contextual value assignments, we restrict to subsets of Pauli observables for which there do exist non-contextual value assignments, and we allow that to define a point in phase space as well. So to be more clear, we restrict to a subset satisfying these two conditions. The first one is just a closure property, and second one says explicitly that we need a non-contextual value assignment function to exist for that set. And then our phase point operators look like this. So rather than summing over all Pauli observables, we only sum over the ones in that set. And so now we have two parameters, germinative point in phase space, a non-contextual value assignment, as well as a set over which it's defined. And then the Wigner function is defined in the same way as the coefficients in this expansion. So this phase space also has nice properties for describing QCM. So phase point operators map to phase point operators under Clifford group operations, and they map to probabilistic combinations of phase point operators under Pauli measurements. And so positivity of the Wigner function is preserved under both. And again, we get a classical simulation algorithm based on these phase point operators. It works in the same way. When the Wigner function of the input state is non-negative, you sample from it and you obtain a phase point operator, and then you propagate the phase point operator through the circuit using the update rules. In this case, the measurement outcomes are a bit different because we don't have deterministic outcomes for all Pauli observables. When your Pauli observable is in the set, just return this non-contextual value assignment. When your observable is not in the set, you just return +1 or -1 of the equal probability. And we get the same conclusions from this simulation algorithm. So negativity in this Wigner function is a necessary condition for a quantum advantage. I guess I don't have a geometric picture for that one, but it's the same idea as before. So now we can ask this question: what do these simulation algorithms have in common? They all start in the same way. So it's just a rehashing of those conditions that define the quasi-probability representation. So we start by defining a set of phase point operators. We'll find a set of operators in this Hermitian operators with unit trace. And then we make sure that they behave well under Clifford group elements and Pauli measurements. And then the states for which these simulation algorithms apply are the ones inside the convex hull of these phase point operators. So I was kind of hinting at this the whole time, but there's another way of interpreting this, a more geometric picture, a geometric way of interpreting this. So rather than defining a set of phase point operators, we start by defining a polytope. We identify the phase point operators with the vertices of the polytope, and then we ensure that the polytope behaves well under all the dynamics. So basically, the polytope has to map back into itself under all Clifford gates and Pauli measurements. And then the set of states for which the simulation algorithm applies are the ones that are contained inside the polytope. So the question we can ask now is, how big can we make the polytope while still preserving property number 3? We're going to make the sort of contain as many states as possible while still behaving well under Clifford gates and Pauli measurements. And we have an answer to this question, which is you get this set here. So this is what we call lambda polytopes. It's just the polar dual of the stabilizer polytope. So it's a set of all operators in this trace 1 affine subspace of the vector space of Hermitian operators, satisfying these inequalities. So for each stabilizer state, you have this trace inner product is non-negative. So this set defines a polytope. Now, this polytope has a finite number of extreme points. We identify these extreme points with phase point operators, and then we make sure that we have the required dynamical properties. So first, under Clifford gates, the polytope maps back into itself. Same thing under Pauli measurements, and then we have this fourth property, which distinguishes this from the quasi-probability representations from before, which is that this polytope contains all quantum states. all n-qubit quantum states. So a consequence of this property number 4 is that any state can be represented as a probabilistic combination of the vertices of this polytope. You don't need any negativity in the representation. And then for dynamics, we have the same properties as before. Phase point operators map to other phase point operators under Clifford gates, and they map to probabilistic combinations of phase point operators under all Pauli measurements. So everything here is probabilistic. There's no negativity required anywhere.
But can I ask real quick?
Sure.
So the phase point operators themselves, though, aren't always positive.
You
I
mean
mean, I suppose that,
as operators?
yeah, it's operators.
That's right. Yeah, yeah.
And I suppose, well, first of all, are any of them positive? Or
No.
in the case that none of them are positive?
In this case, none of them are positive.
Okay. So, I mean, does this affect in any way, though, your Pauli measurement update rule? Because, I mean, you have this kind of condition that, like, on the previous slide.
Yep.
Yeah, this trace x pod.
Yep.
Is positive. Oh, but I guess this is a Pauli projector.
Exactly. Yeah.
That's a stabilized state.
So
Okay.
yeah, this does require we restrict the allowed measurements.
It was
So-
positive to the Wigner function either, right? The odd one.
That's true. Yeah.
They
So
were those
yeah, odd dimensional Wigner function for the CNC thing that I was talking about earlier.
Yeah.
Those phase point operators also aren't positive definite,
Yeah, sure.
but for Pauli projectors, they do
Yeah,
get
that
positive
quantity
values.
will-
Yeah.
Okay, great.
Okay. Yeah. So because every state is inside the polytope, we get positive representations for all states. Dynamics are also positive. So everything is probabilistic here. And we get a simulation algorithm, same as before. So we start by representing the input state as a probabilistic combination of the vertices of the polytope, and then we sample from this probability distribution to get a vertex, and then we propagate the vertex through the circuit. We have a deterministic update rule when we come to Clifford gates, and a probabilistic update rule when we come to Pauli measurements. Yeah.
So if you want for people get control measurement for place divided by one.
Yep. Yeah. So we have this restricted set of operations with Clifford gates and Pauli measurements. That's enough for universal quantum computation when you put in alpha states as well, right? But here, every state is inside the polytope.
Oh, okay. So automatic state of entire event can do not any computation.
Exactly. Yeah. You can simulate any computation. Yeah. So yeah, when you come to Clifford gates, you have a deterministic update rule. When you come to Pauli measurements, you sample from this probability distribution, and you get two things. One of them is a measurement outcome, and the other one is your new phase point. This is this probabilistic update rule for Pauli measurements. So here again, we have a geometric picture. So in red is quantum states. Inside a set of quantum states, you have the stabilizer polytopes. This is this diamond shape. And then the polar dual of the stabilizer polytope is this lambda polytope. And as you can see, stabilizer polytope is inscribed inside the set of quantum states. And then our lambda polytope inscribes the set of quantum states. So every quantum state is inside the lambda polytope. So unlike before, this classical simulation algorithm applies to QCM on any input state. So you could use a simulation algorithm to simulate any quantum computation. However, we don't expect this simulation to be efficient in general. So there should be some cases where, although we can simulate it, it's not going to be efficient. That said, there are some special cases where classical simulation is efficient. So for example, in the case of multiple qubits, these CNC type Pauli phase point operators that I defined earlier, these are vertices of lambda. And in odd dimensions, these phase point operators that come from Gross's Wigner function, these are also vertices of lambda. So for example, if you have an input state where the support of the probability distribution representing the input state is restricted to operators like this, then you do have efficient classical simulation. And this gives us a pretty clear path forward, which is to characterize more vertices of this polytope. The reason being, if we can do this, we can kind of expand the scope of efficient simulability. So this is our path forward. this is what we want to do next. So we do know some things about the lambda polytopes. So for example, if you have a vertex A sub alpha, you can kind of tensor on projectors on the stabilizer states, and maybe conjugate by a Clifford gate. The result is still a vertex of a polytope on more qubits. So in some sense, tensoring on stabilizer states doesn't increase the complexity of classical simulation. We can also do numerics. The problem is numerics is kind of hard. So for one qubit, it's easy. We're in a three-dimensional space, and the lambda polytope is this cube. So it's got 6 faces and 8 vertices. They're pretty simple. But even by the time you get to 2 qubits, we're in a 15-dimensional space. Lambda polytope has 60 vertices, or sorry, 60 facets and 22,000 vertices, which fall into 8 orbits under the action of the Clifford group. And then for 3 qubits, we're already in a 63-dimensional space. We have over 1,000 facets, and we can't even count the number of vertices. So numerics is already very hard. Yep.
For the number of states inside the polytope.
Number of form states.
Yes, how much from the vertical space inside the sufficient is right for polytope?
Oh, I see. Yeah, we do have some numbers. Maybe that's something to talk about later. Oh, okay, we got it. Yeah. Yep.
Suppose somebody gives you a vertex.
Yep.
You know how to tell if it's like
If it's one of those ones that I talked about earlier, the next, in general, if it's something else, then not really, that would take more work.
So then I not quite understand what do you mean by characterizing vertices.
Okay, so basically vertices fall into different orbits under the action of the Clifford group, and it's these orbits that are efficiently simulable. So, for example, so these phase point operators from Gross's Wigner function, they're one orbit under the action of the Clifford group, and they're all efficiently simulable for any number of qubits or qudits. If we can characterize more orbits, which have efficient update rules, because this is a property of the orbit, not of a given operator, then we should be able to simulate more.
Okay, so suppose somebody gives you a full orbit.
Yep.
So is there like a way to tell what was efficient with simulable?
In what format are you giving it to me?
Excuse me?
In what format? Like you just giving me the expansion coefficients and Pauli basis? Or something like this?
Yeah.
So you can compute update rules numerically. It's just solving a linear programming problem.
So it's like if somebody gives you an orbit, you just like check if you can sample or not. What do you do?
Yeah, maybe that'll be the first step is to do the numerics, compute the update rules numerically, and see if we can break down simple versions of them. For example, these ones, you always, if you do a Pauli measurements on one of these vertices, you always end up with just a weighted combination of 2 different vertices. You don't end up with more. The problem is, in general, you could have an exponential number of terms in sum rather than just 2. The question is how many terms appear in that sum, or that's part of what determines the complexity.
So if you have many qubits,
yeah,
I would assume that you also would have like extremely many orbits.
Yeah, that's possible.
Yeah, and then like, do you just tell that like so many classes and I mean like I kind of wonder what do you mean by characterization? Is there like also exponentially many orbits?
That's something we don't know. Yeah.
Oh, well, we know that there's more than exponentially many orbits.
Yeah.
Orbits or vertices?
Vertices.
It seems like it would be a linear number, like the number of orbits could just be linear, right?
Could be.
I mean, it's only 8 with 2 qubits.
Yeah, so do you fold the U orbits, or is it like a big fold orbit?
It would be nice if there were few. The problem is we really don't know very much about scaling at all, because we can only do numerics for 1 to 2 qubits. 3 qubits is already very. So we can't really say very much about the number of orbits right now.
So if you allow me thinking by analogy, there's this like problem of characterizing many body entangled states.
Okay.
And for 2 bodies, you have maximally entangled state. For 3 bodies, you have like 2 classes. And for more than that, you have like infinitely many classes. So of course, you will not have infinitely many classes, but I mean, like that would be somewhat an unsettling result, right? In the characterization attempt, if you would have like,
it is possible that we have, doubly exponentially many orbits, in which case you wouldn't even have an explicit way of writing them all down, the exponential number of bits. So you wouldn't be able to simulate everything efficiently anyway. But anyway, that's something we expect. We don't expect to be able to simulate everything efficiently. It's just the more vertices we can characterize, the more we can simulate.
I would like to make a correction to that. I mean, at least for the qubit case, I don't know for the general case. And yeah, so the question is not the number of vertices, the number, the logarithm. So it's like with phase space. They have exponentially many points, but you can describe it with 2n bits. That's kind of the first thing you look for. And so, well, we believe maybe the number of vertices or logarithm of the number of vertices is very large, scales very badly, it's possible. But from the simulation point of view, the question to ask is not how many vertices are there in the polytope, but because the magic state is always the same. Yeah. How large is the set of vertices that you can reach from the magic state? And that's going to be smallish.
Yeah, so it's connected to this, like how many orbits? Like how many things you can do.
No, it has something to do with that.
Okay.
But it is. Yeah, I mean, yes, I mean, I don't know. I wouldn't say so. I mean, you need to know exactly the vertex where you are at a given moment to know which orbit you are in. Doesn't help. You need to know where exactly in the orbit you are. You need the full information.
Okay.
And so, yeah, presumably the number of vertices is going to be too large. But the question is, since in magic state computation, you always start from the same state. The question is, in the computation, can you reach all of the vertices that the polytope has? And one can show that this is not the case. And the region that you can reach is comparatively small.
And you want some kind of characterization of the region?
The size, you want to know the size. Well, maybe also characterization. Yes, maybe more. I mean, it could be that the hardest vertices you update are those that are never reached. It's a possibility.
So it's kind of the same kind of story, but from a very different perspective. That, like, I guess people talk about physical corner of the Hilbert space, this like area law and entangled state and things like that. So you also want the physical corner of the Hilbert space of the both was not a Hilbert space.
You can think of this.
I mean, I would say yes.
Okay, thanks. Thanks a lot.
Yeah, I was just going to ask something kind of along these lines. For these 8 orbits, can one think of this as some sort of a classification of 2 qubit magic states? On the states that I can form from convex combinations of. purely vertices in these 8 orbits somehow.
So the orbits themselves, like the phase point operators associated with the orbits, they don't map directly to states. 'Cause
Yeah,
they're,
sure,
they're not positive, right?
Uh-huh.
You want to get some kind of magic states out of the operators.
Mhm.
Sure. I mean, you can sort of deform them until they are positive, and you get some kind of magic states out of them, maybe.
Uh-huh.
I'm not sure what you mean by classification of magic states. 'Cause
I
you
mean,
could
I
have
guess it's just
interpolation
that you
between
can, from what I understand from the orbits, is like I can never get to a vertex in a different orbit by applying Clifford gates.
Yeah, that's true.
From one orbit to another orbit by just applying Clifford gates.
Yep.
Sort of, I don't know, to me it almost says something like it's kind of different degrees of magic states.
Yeah, but again, you had to modify the operator somehow to make them
Yeah,
positive.
yeah, sure.
You know, like it
sure,
states,
yeah,
and that might change some things.
sure.
Okay, so, yeah, it's possible. Maybe we should talk about that more later.
Yeah.
Yeah, thanks. Anything else? I'm just about to wrap up now anyway. So yeah, the point of what I'm trying to do today is not really to give you everything in full detail. You can refer to the papers for more details. It's more to give you motivation, kind of overview of how we use these polytopes, and also to kind of advertise them, because we think they have a lot of interesting structure, and we think more people could be interested in them. So I'll end there.
So in this polytope, so can you find like magic state, like this state, and quantity state? So it doesn't scale probably, but like how much magic you can find inside?
I'm not sure I understand the question. So the magic states are inside the polytope?
So in the efficiently simulatable, right? If you
Okay,
take
yeah.
like 3 qubits, you may find like 1 T probably or something like that. But if you scale the qubits, how much T state do you expect to find?
Yeah, so for example, you just look at the subpolytope and the CNC type phase point operators. For a couple of P6, you're still inside the efficiency rule part, but as you add more P6, you do end up outside. For three P6, for example, you're already outside this CNC subpolytope. This would be the goal. You have more vertices. Maybe you end up with more P6 inside the efficiency part.
But currently, do you think this is a constant number, or it should scale somehow, maybe very, very slow, if like the number of qubits?
What quantity is scaling?
So here you show numerical simulation of 1 qubit to 3 qubit is an n qubit. So I want to find like key state, I guess. So would you expect it to be constant in number? So like depend on the number of qubits at the end, or do you expect it to grow with like something very slow, so maybe I don't know, like slow function?
You're talking about these robustness measures?
So I'm asking for like the number of T states or A states that you can find for n qubits inside the efficiently simulatable polytope.
Yeah, that's going to be fixed. So, like,
Okay,
2 qubits is inside, for 3 copies of the sticker outside. But it kind of depends what you take to the efficiency and what point.
okay, so one thing is like fixed, and you cannot expand the polytope to
Yeah, so this is the goal. By coming up with efficient that it goes to more vertices to kind of expand this.
Oh,
But it's unclear how much you can expand.
one thing like three that already outside, so 2 would be like more number outside.
Yeah, so for 2 qubits, all magic states are inside. And for 3 qubits, there are magic states outside the efficiency local part. And there can be some negativity to only use those efficiently available phase point operators. And so we still get some simulation, but it's going to have this In general, exponential numbers and squared.
Yeah, maybe I'll ask a more specific question, that maybe you have an answer to. Is it the case that all stabilizer states can be described as convex combinations of vertices in one particular orbit?
Yes, that is pretty easy to do. Yeah.
Okay.
Yeah. And yeah, you can describe any stabilizer state as a probabilistic mixture of C and C type vertices.
Yeah.
From one orbit.
So can I think of another orbit as all states that maybe have a one T state with the magic in there? In another orbit, or well, maybe the question.
Yeah. So you can think of something like that. It's related to this idea that I said. So if you tensor on stabilizer states,
Yeah.
you still get vertices.
Yeah.
So you can think of like a sort of magic part
Yeah.
with a sort of classical tail on it.
Uh-huh.
So for example, if you take a set of all 2 qubit phase point operators here and tensor on the 1 qubit stabilizer states, you get a 3 qubit subpolytope,
Uh-huh.
right? With 1 qubit worth of classical stuff and 2 qubits worth of magic.
Yeah.
You can take something like this. Yeah.
So I mean, yeah. Yeah, there's stabilizer states. You can have 1 T state. You can have 2 T states. But I guess what do the other 5 orbits correspond to? I mean, I guess for the second 2 options, I guess it's not clear whether
Yeah, it would take some more work to.
states that are convex combinations in one orbit correspond to that.
Yeah.
Yeah. Interesting.
Any more questions? Nothing in the chat.
Yeah, well, that's the case. Thanks, Michael, again.